Good evening, students. Let us start with the extrinsic type semiconductors. So we have already seen what are intrinsic type semiconductors. In the intrinsic type semiconductors, it is temperature dependent. When the temperature increases greater than 0 Kelvin, then only the bonds break and they liberate the free electrons to move. So we see that the conductivity is very much less. So what we do in a crystal, we add the impurities, and as soon as we add the impurities, the conductivity increases. So what is doping now? Let us understand an important term, which is doping. What is doping? Doping is the concept of adding impurities deliberately in the pure crystal in order to increase the conductivity. So what is doping? Doping is adding of impurities, all the impurities which we add in it in order to increase the conductivity. But the main concept over here is that what type of impurities should be added. The type of impurities which should be added should be such that it should have the same size or nearly the same size of that of the pure crystal. So the first concept which comes over here is doping. So what is doping? Doping is adding of impurities to the pure semiconductor in order to increase the conductivity. So addition of impurities. To pure semiconductor to increase conductivity. So this method is known as doping, and the crystal in which the impurities is being added is known as the extrinsic semiconductor. Now there are two types of dopants, the materials, the impurities which we are adding deliberately in the pure crystal to increase the impurity, that are known as the dopants. Now there are two types of dopants. Are there. The first type are the pentavalent dopant, and the second one are the trivalent dopant. Okay, in the pentavalent dopant, the valency will be the impurity valency will be 5, and in the trivalent the impurity valency will be 3. The examples of pentavalent dopants are phosphorus, antimony. Okay, trivalent example are aluminium, boron, etc. Okay, so these are some of the examples of adding into the pure impurities to the pure crystal in order to increase the conductivity. Now let us start with the N-type semiconductors. So extrinsic type semiconductors are two types of semiconductors, N-type and P-type semiconductors. Let us start with the N-type semiconductors, in which the pentavalent impurities are being added. So the N-type semiconductors we will be starting. N-type semiconductors. Okay, and the impurities in which they are added are pentavalent. So this is the second type of semiconductor, extrinsic semiconductor, and in that extrinsic semiconductors, again they are divided into two types, P-type and N-type semiconductor. So let us start with the N-type semiconductor, in which type of impurities are added? Pentavalent impurities are added. Now you can take any crystal, germanium or silicon. Here I have shown the germanium crystal, pure germanium crystal, in which I have added antimony. Antimony impurity, which is of pentavalent impurity. So these red dots are the electrons, valence electrons of the germanium atom, and these green dots are represented for the antimony, are represented for the antimony electrons, valence electrons. So it is having 5 valence electrons, as the name suggests, pentavalent impurity. So it is having 5 valence electrons. So the 4 of the electrons share the bond as usual, which the germanium crystal were having, a germanium atom were having, and they were sharing the bonds. So 4 of the electrons share the bond and they form the covalent bond, but the 5th bond is very weakly attached to this atom, to its parent atom, antimony. It is very weakly attached to this parent atom. Okay, now it requires very less energy. It requires very less ionization energy. The energy required to remove this electron from its parent atom is known as the ionization energy, and it is very much less required over here in the case of germanium. In the case of germanium, it is very much less required. So in the case of germanium, the energy which is being required is somewhat equal to 0.01 electron volt, and it is nearly equal to 0.05 electron volts in the case of silicon. But we have taken the germanium crystal. So for the germanium crystal, the energy required to remove this electron from the parent atom is 0.01 electron volts in the case of germanium, and this is the germanium crystal. In the germanium crystal, we have added the antimony impurity, which is having the valency 5, so it is a pentavalent impurity. Now this electron is free to move as soon as this much energy it is being provided is required, and as soon as the ionization energy is being given to it, it gets removed from this parent atom, and now this is free to move in whole crystal, and so this will support the conductivity now. Now the conduction will be with the help of this free electron which I have removed it from its parent electron, and also the conductivity will be from the breaking of the bonds when the temperature rises. When the temperature rises, some of the bonds will get breaked up and they will liberate free electrons. So mostly my conduction will be from the electrons as compared to the holes. The holes will be also formed, some of the electrons will break and the holes will be also formed, but the formation of the holes will be less in compared to the formation of the electrons, because electrons are we are getting from both the sides, from the intrinsic semiconductors which are breaking from the breaking of the bonds, as well as from the impurities free electron, So in the case of extrinsic semiconductor, N-type semiconductor, the concentration of electrons is very much high than the concentration of the holes. It's very much high than the concentration of the holes. Naturally, the rate of recombination will be also high because the concentration of electrons are very much high. So the rate of recombination will also be high. So the rate of recombination will also be high in the case of extrinsic type semiconductor. Now this type of impurity is giving one electron. So the pentavalent impurities is said to be as donor impurity. It is said to be as donor impurity. Pentavalent impurities are known as donor impurity. Donor, because they are donating their one electron for the conduction. They are donating their one electron for the conduction of the electrons. They are donating for the conduction. So one electron is donated by the impurity atom, and the impurity atom is the pentavalent atom, and which is here I have taken the case as an example as antimony. You can take it as any of the impurity. Okay, so it is known as the donor impurity. It is known as the donor impurity. Okay, so let us see now how the bands formation takes place, the valence band and the conduction band in the case of extrinsic type semiconductors. So let us draw the bands. This is conduction band, we see. This is valence band, VB, and this is VD, 0.01 electron volts. This is VD is but nothing but the donor energy level. VD is nothing but the donor energy level. So what is VD? Donor energy level. Okay. Ag is the gap. So the electrons here, there will be electrons in the conduction band also. Some of the electrons will be of the impurity atom, which are donated by the impurity atom, and some of the electrons will be with the by breaking up of the bond, so leaving behind the holes, okay, leaving behind the holes. So in this case, the concentration of electrons is more than the concentration of the holes. So such type of semiconductor is known as N-type semiconductors, because the concentration of electrons is more than the concentration of holes, and the rate of recombination is also high. Okay, and so in this the pentavalent dopant is used, pentavalent impurities are used. In the pentavalent impurities there is one extra electron which has very weak bonding with the parent atom, so it requires the ionization energy, and that ionization energy is very low. So as soon as it gets the 0.01 electron volts, in the case of germanium, it detaches from the parent atom and it starts moving in the crystal. It starts moving freely in the crystal, and as soon as it starts moving, it helps in the conduction. And as soon as the temperature increases from the 0 Kelvin, some of the bonds break, liberating the electrons. Suppose if this bond breaks, liberates the electron, so it will create a hole over here. It will create a hole, and the electron will move. So some of the bonds break, and so we see that the number of electrons concentration is more, which is helping in the conductivity. So this type of semiconductor will naturally have more conductivity than the intrinsic type semiconductors. Okay, so in the next session we will be studying about the P-type semiconductor, which will be having trivalent impurity, and that type of impurity will be known as acceptor impurity. Okay, so thank you. Please share my videos, please subscribe my channel, and if you have any doubt, you can ask me in the comment section. Thank you.